Thanks to Doug and the crew for inviting me down and somehow wrangling me into giving 2 talks. But I was really stoked to see Ron's talk, and I'm really excited to use the chainsaws down in Colorado this summer. We are actually going to go down there and try and tease out some of those return periods of some of those slides in various areas. So stay tuned for what they really are. What do you think, Ron? How many years return periods were some of the larger ones?
Looks like sound of the big one over 100 years.
Okay. I've heard from others upwards of 300, maybe even 500-year cycles. Yeah. When you talk to the old guys like that are 200 years old, then yeah, it makes sense. Ethan only being 100 years old, it doesn't matter. So, all right. So I want to acknowledge collaborators on this project. My supervisor, Dan Fagry, Greg Peterson, who works for the USGS here, Yordi, everyone knows Yordi, and Carl, and then the techs that helped us in the field, Adam Clark and Danny Stully. So we went out with the intention to try and answer these 2 questions with this project. What's the frequency of large magnitude avalanches in northwest Montana, and what sort of climate or atmospheric variables drive or influence these large magnitude avalanche years? And when I say large magnitude for the purposes of this project, we define it as a size D3 and above, and as Ron pointed out, that might be subjective now. It all depends on your perspective and how long you've been around. So for those that aren't familiar, dendrochronology is the study of tree rings, and it can be used to study all sorts of landform processes, anything from landslides to obviously avalanches. People use tree rings to study climate. You can look back and look at the width of the tree ring, and it gives you an indication of precipitation and temperature. But again, we're using it to study D3 or larger avalanches, and here's a great example of a avalanche from 2009. I believe we classified it as a 4.5. What's the difference between a 4.5 and a 5? So we went into 12 avalanche paths and collected almost 700 cross sections, and I'll show you the cross sections in a bit here. And for those that have seen and heard this presentation or a modification of it, I apologize because I'm going to use the same jokes. But we sampled in 4 different mountain ranges in northwest Montana. Here in Glacier Park, we sampled, got 232 samples in the central part of the park along the Going to the Sun Road, for those that are familiar with that area. And then along Highway 2, there are a number of avalanche paths that affect both the railway, BNSF railway, as well as Highway 2 itself. So we sampled 3 paths there. Then we went into the Whitefish Range up in the northwest part of our map here, and sampled in the northern Whitefish Range and then in the Swan Range. And those 2 areas aren't, they're popular backcountry recreation areas in the winter. So we wanted to get a sense of what the return frequency was for those areas where we just can't, we don't get many observations, especially historical observations. So here's just a few images of some of the areas. This is John S. Stevens Canyon along Highway 2. And then, of course, the Going to the Sun Road. Those are some of the avalanche paths that affect the road. So this is what we're looking for. When we're out in the field, we go tromping around with our chainsaws. And we're looking for samples that, if they have a scar like this right here, that's great. Then we'll cut into that and get a nice slice out of that tree. And you can see here, I'll just point to it. The arrow here is pointing to the uphill side, and it's pretty obvious that year after year we get avalanches hitting this sample in particular. And here's a little video the Park Service did about some of this work. This right here we suspect could be an avalanche scar, but what we do is then we cut into this dead and down tree and then take a thin cross section from this tree. And then we can take that to the lab, process it by sanding it, looking at it under the microscope, counting all the rings, and then cross-dating it. So we take these samples, and it requires a lot of work. And some folks might be wondering if you've heard of this work before, if you've done some of it yourself. Why don't we just use cores? Cores have been used in a lot of dendrochronology work. They're again used in for studying climate. But when we're studying avalanches or any sort of geomorphic disturbance, imagine taking in this sample, let's say we took a core, and we can take, let's say, 4 cores in 4 different cardinal directions on the tree. But if we take a core here, and maybe one over here and over here, we might actually miss, and this is a large scar, so we're probably not going to miss it in this sample, but we might miss the actual signal, and so that again biases our record and our chronology. So here's a good example. This is a scar from 2003, which is a big cycle in the region. Imagine if you took one here, one up there, one over there, and maybe even one over here. You would completely miss this scar. So cross sections are really, really important. A lot of previous work has used a mix of both cross sections and cores. But again, the cross sections provide the whole complete picture. So we have, in terms of cross sections, we have about 650, and 509 of those are class 1 and 2. What do I mean by class 1 and 2? So we have a 5-scale category when we classify these scars. Class 1 is your best signal. So an avalanche hits a tree, it actually leaves a physical scar that looks like this. We can also have reaction wood. So if an avalanche hits a tree, let's say this is the uphill side, we can then get, on the uphill side, those rings would become pretty thin. On the downhill side, those rings would actually get larger during that year and subsequent years to sort of buffer the impact from the avalanche on the uphill side. So a reaction wood, if we have pretty strong reaction wood signal, might be like a class 2 or 3. When we get down to class 4 and 5, there might be some reaction wood. It's sort of hard to tell. But again, those like class 1 and 2, and even some 3, they're usually associated with strong reaction wood signal and associated with a scar as well. So most of our samples, fortunately, are class 1 and 2, which is good for us. It means that we have a pretty robust data set. And so again, we have about 700 samples, but within each sample, there could be any number of growth disturbances. So that means, a scar, reaction wood, those sorts of signals. So we have almost 1,300 growth disturbances of class 1 and 2, and 2,300 growth disturbances in the entire data set. So our samples went back. What we do is we take the sample, and if you know when a large avalanche cycle or a large avalanche in any given path occurs, then we're pretty certain, let's say, for instance, in 2014, we knew that we had a big cycle, went out, collected a bunch of samples in 2017 after another large cycle, so we were pretty confident about that. But what we need to do to actually make sure, and when we go to paths that we're not sure when these, a bunch of these trees fell down or got taken out, then we take the samples and compare them to the chronology or the rings from trees outside the avalanche path. We call that the gallery forest, and basically correlate the size of the tree rings. So it gives us, it's called cross dating. So it gives us a really good sense of when we can date each year in every given sample. So we can go all the way back to 1636 for our samples, and the mean age is 73 years. So we have a pretty good, chronology here, going back that far. In terms of species, most of our species were subalpine fir in northwest Montana. We also had Doug fir, and then some Engelmann spruce, and then a number of others. I'm not a tree guy per se, so a bunch of other 4-letter acronyms, Latin acronyms that I don't remember. So here's our raw response. This means that all of our responses, no filters applied whatsoever. And again, going back to the mid or late 1600s here. In this case, these are our responses. So our trees go all the way back to 1636, but the first avalanche response shows up about the mid 1600s. The problem here, of course, is that we don't have many trees. That's the problem with studying doing dendrochronology and avalanche paths. That the avalanches actually take out the trees, and you might not be able to capture that signal when there are avalanches because there are no trees to record it. So we then have more avalanches in subsequent years or more recent years. So how do we get around that? How can we tell if it's an actual avalanche year? And what we're trying to do is figure out the signal. So what is an avalanche year and what is just a bunch of noise? So we do that 2 different ways. We do a threshold per path. So every given avalanche path, we have a variable threshold based on the sample size of that path. And we take basically the number of trees exhibiting a growth disturbance per trees alive in that given year, and a minimum number of samples in that given year. So that's one way we sort of suss out the lack of trees from far back. Another one is we weight the more heavily, the higher quality indexes. So the class 1s and 2s are weighted more than the class 4s and 5s. So we apply both of these to our samples, and of course some get filtered out. And so now we have chronology that goes back to about the mid-1800s after applying this pretty stringent filtering system or threshold system. So this approach is sensitive, or the results here are sensitive to our approach. We have 32 avalanche years when we use the weighted index approach, and we have 37 avalanche years when we use the percentage and the number of given trees, minimum samples per year. So pretty close to each other. So when we use both thresholds, it works out pretty well. We have 65 avalanche years without a threshold per path. I'm using the first step. So if we don't use that first step right here of the threshold per path, it might just be a bunch of noise. Those avalanche years might not be real avalanche years. So from our tree ring chronology, these are our notable years, meaning that a lot of class 1 and 2, this is from, again, both thresholds combined, but these are our notable avalanche years. So if we didn't apply these thresholds, this is what it would look like. These are the percent of trees scarred per the number of samples for that year. So we have 2 samples from, say, 1636, but both samples have avalanche scars from that year, but those are the only 2 samples that we have. So we can't just use a percent. So we're saying here that one scarred tree doesn't really mean that we actually have an avalanche. We sort of, there are other disturbances that create these signals as well, so these scars and reaction wood. But we basically targeted these avalanche paths without these other disturbances. So rockfall, landslides, that sort of thing. And at least to our knowledge, we haven't seen landslides in these areas. They were away from areas that can contribute rockfall. So we're pretty confident, very confident that they are avalanche signals. So in terms of our return interval across the entire region, so this is all of our avalanche paths combined, we came up with a mean return period of about 3 years. So that's, again, just pooling all of our paths together and coming up with about a 3-year return period of large magnitude cycle. But when we look at each path individually, there's quite a bit of variability. So what we have here on the bottom is our path, and then over here is our return interval year. So this is the black lines in each of these boxes is our median. It's our central value. And this is the 50% of our data per path. So this is the middle portion of the data. So here we're looking at, if we take, for example, in Glacier Park, which is the central part of the park, which is dark gray, our 54.3 along the Going to the Sun Road, has somewhere between a 15 and 20-year return period. But then if we go to a path on the east side of the Continental Divide, we have almost a 30-year return period over here with quite a bit of variability in our samples. And then if we go over to, let's say, somewhere in the Whitefish Range, where the paths are considerably smaller, then we have a much lower much higher return frequency. So there's quite a bit of variability. So when we group them together as a region, that's our next step in some of this work, is trying to figure out what does region actually mean. So from the tree ring record, our notable avalanche years all had above average SWE. They all had below average temperatures, except for 1 year of 1971, which was average. Now we compare it to the historical record. And so when we compare it, it's kind of variable. The historical record really only comes from, the longest record comes from John F. Stevens Canyon in the southern part of the park. And in the southern part of that park, or of the park, the records go back to, some of the records actually go back to like the early 1900s, but the records aren't robust. They're from, say, highway workers or railway workers that might see a slide. But again, they're only recording the biggest slides, the ones that actually affect or come close to the railway or the road. And so, for instance, in 1950, this is one of their great observations. This is all we get. Trouble, trouble. These are the only words to describe the Middle Fork this past week. So that's all we have. We don't know how many slides. We don't know where they were. So, when we talk to some of our colleagues in Europe, and they have historical observational records that go back to like, you know, the late 1700s, early 1800s. Ours go back, robust records, really good, you know, forecaster records go back to the late 1990s. So there's a bit of a discrepancy there. So this is why we're doing tree ring work here. So 19 of 27 years have average or above SWE, and this is right up here. There is a significant difference between non-avalanche years and avalanche years when we're looking at SWE. This is no surprise, right? We get more snow, we're going to have more avalanches typically. However, and we all know this in this room, is that we can have large magnitude years. You can see the triangles below the green line. We can have large magnitude years in low snow years. We develop a weak snowpack because of that low snow year. One storm, any one given storm, of course, can make or can give us a large magnitude event. And that's one of the limitations with studying tree rings, is that we're looking at an annual scale. It's not like we can boil it down and say, oh, there were 4 big cycles in 2011. We can only say that there was at least 1 big cycle in 2011. And then, you know, on the low snow years, again, it's still the same thing. We can only say that there was at least 1. So what we did is we took a bunch of variables that might influence some of this, some of the large magnitude years. Like we did all sorts of, we did 500 millibar levels to look at, you know, some sort of storminess index. We looked at El Nino southern oscillation, so El Nino La Nina. We looked at the Pacific decadal oscillation, which is more of a multi-decadal signal atmospheric circulation based on sea surface temperatures in the North Pacific. And we also looked at snow, a few snow variables like SWE, snow depth, and then of course temperature. So we basically put it all into a bowl, did something called a principal component analysis, and our first component teased out as an interaction between El Nino and PDO, which makes sense. Those two are pretty well interrelated, and that explained about 42% of the variability of our large magnitude years in a time series. Our second component was snow depth and maximum temperature, annual winter maximum temperature, and that explained about 13%. So over half of our variability can be explained by atmospheric circulations, snow depth, and max winter temperatures, so the combination of all of these things. Again, no surprise there, but what we're trying to tease out is what specific interactions. And it turns out that a negative PDO index and negative El Nino, which is a La Nina, at least again for northwest Montana, is set up there with a La Nina during negative PDO phase. Typically means low pressure over the Pacific Northwest, high pressure in the North Pacific, and typically translates to above average or above normal snowfall in the Pacific Northwest. So things are lining up really well. It actually, you know, in terms of our results, and it sort of makes sense. So the other component to this work, aside from the climate analysis, is the spatial analysis, looking at avalanche return periods. So actually Blaze and Greg Peterson and others did a paper looking at return periods in one of the paths in Southern Glacier Park, and used a technique called kriging, or another similar technique is inverse distance weighting. So it's a spatial interpolation. So you basically take any one given tree, and this tree, let's say the return period here is 30 years, and this one is 30 years. So it sort of takes the average and weights, you know, spatially all of your samples, and then extrapolates from there. It's a pretty effective technique, but the problem is when you take it on a variety of paths, and this is one of our paths in the park. That's the starting zone up there. So you can see the blue return frequency is obviously higher in the starting zone on some of the samples we collected way up high. But then when we collect samples way down low, we see sort of this weird artifact in between here, and that's clearly not real, at least not in that pattern. At least we have, you know, lower return frequencies way down at the bottom, but some folks did some recent work, and this is looking at, you basically delineate where avalanches have occurred instead of sort of just applying a big broad polygon like this one. You basically tease it out a little bit more, define it a little bit more based on observational records, and there you're going to get a much more realistic recurrence interval by doing this. So some of our conclusions in our return interval is roughly 3 to 4 years. It was like 3.5. Our atmospheric connections, large magnitude avalanches, are characterized again by those above average SWE years, as well as snow depth. PDO, Pacific Decadal Oscillation, and ENSO, snow depth and maximum winter temperatures were the largest drivers, at least in the analysis we've done so far. We still have more to do. We're still continuing this. But again, caution inferring a climate signal with avalanche phenomenon and climate change. As we all know that, as I mentioned previously, any one given storm can create, depending on the snowpack, can create a large magnitude event. And so we want to be sure that we're actually being really robust in the analysis when we're trying to infer any sort of climate signal out of this. So our next steps are, we only have weather and climate records that go back to, in our region at least, back to the early 1900s at best case scenario. Our avalanche records from the tree ring go back even further. So what we're going to do is use reconstructed snow water equivalent and temperature records to extend that climate chronology back, which has already been done by others. That'll allow us then to at least get a longer time series out of it. And then we'll do a trend analysis with our longer record to see, are we actually seeing more avalanches or fewer avalanches? Or is it staying the same? Is it just there's just too much variability? And then creating our return interval maps for every single path, and then answering the question of what does regional actually mean. So what I mean by that is, a lot of the work that's been done in the dendro field with avalanches, it's just basically been one path or several adjacent paths. And so there really isn't a context for return periods for an entire region and what that actually means in terms of climate or long-term atmospheric influences. So it looks like we have a little bit of time for questions, and with that, I'll take those if there are any. Thanks.